The changes between the two time points of the sample can be quantified. And the most basic way is to create heat maps of cell growth and proliferation. And this will correspond to the change in area of cells and number of cells over the time point. And for this to work, it is important that the parent labeling is perfect. So mistakes will appear as outliers in the growth map, and they are very easy to spot. And it is very unusual for lineage tracking to be perfect the first time. So to create the growth map, run the heat map process, load first the meshes you want to compare. In mesh 1, earlier time point with the labels selected. And in mesh 2, you can select parents. And you should see the corresponding cells on both meshes painted with the same color. So now you can run the process mesh heat map with stack 1 selected. And so here you can select the geometry area measure, tick change map, and choose a direction. So if you're visualizing the result on the first time point, then set the change map to increasing to quantify cell area increase over time. And MorphoGraphX will auto-scale the color range to the data and will color the cells with the most expansion in red, and those with the smallest in blue. And also you can create change maps for any kind of data. Simply choose a different measure to create a change map, for instance, for signal average or circularity. And cell division greatly affects the result of the change heat maps. So that by default the heat values of daughter cells are summed up and the change with the value of the parent cell is quantified, which is the appropriate method for cell area. In some cases it might be appropriate to average the heat values of the daughters instead. And this can be done by selecting parent-based heat map and change the drop-down menu to average. Here. So now we can run the heat map. So now, if everything is perfect, you will see a heat map, and usually you will see obvious outliers, individual cells which are more bluer than their neighbors or much redder. In this case it's fine, but we need to change the range. So we need to decrease it, 0 to 3.5. Okay. Now you can see the change in the area from this time point to this other time point, and you can see that the highest increase in area happens in this part, so where this bulge is forming. And now you can create a cell proliferation map, so you can run the process mesh lineage tracking, heat map proliferation here. And this process will work only for stack 2, where you have parents active, so you have to select stack 2, label, and this will display the heat map showing how many cells originate from one parent label. You can basically see the division rate of cells. We can deselect this heat map so that we can see the range for this other heat map. And so you can see that actually the cells in blue have no division, while the ones in red even have 6 divisions. And the divisions happen more on this side, close to this bulge. And after that we can export this heat map, going to attributes, save to CSV extended, and we can call it heat map. And you can select the geometry area and the proliferation rate. Okay. Let's check the file. Okay, and here you can see the change in area and also the division rate, and we can sort the cells by their proliferation rate value. And if we go down, we can see that only few cells divided 2 times, 3 times, and less than that 4 or 5 times. Okay. After that, we can have a look at principal directions of growth. So these principal directions of growth, or PDGs, describe the growth anisotropy at the level of individual cells. So the output of this process are vectors that for each cell give the direction of maximal and minimal growth and can be visualized with white lines on top of the cells. PDGs are computed based on cell junctions, which are the vertices that are at the intersection between 3 different labels. And before we can compute the PDGs, we have to identify which junctions in the second time point correspond to the junctions in the first time point. So, first, if you haven't done so far after the segmentation, you have to fix the corners of the triangle. So if you zoom in, you should not see blank spaces here. If you see these blank triangles, you can run the process mesh, self mesh, fix corner triangles. That is here. And you have to run it for both meshes. And this will make sure that all the junctions between cells are correctly segmented and that there is no triangle in the mesh that is left without label. And after that, save each mesh once fixed corners is complete. After that, you have to find the correspondence between junctions. So since the labels are different between the 2 meshes, you have to load the parents in the second time point. Then run mesh cell axis PDG check correspondence. So first let's put this and run mesh cell axis check PDG check correspondence. And the output should be a color map with cells which are correctly identified in blue and cells causing problems in red. And the vertices from the first time point, stack 1, that could not be correctly identified in the second time point, stack 2, are selected and should appear in red. So make sure stack 1 is active and has mesh lines and points selected, and then you have ticked parents on stack 2. So in this case, everything is blue because we checked it before by running the semi-automatic parent labeling that was also checking the correspondence. And once this process is complete, you can run the process mesh cell axis PDG compute growth directions with stack 1 active. Now you can, after the process is complete, you can display the PDGs using the process mesh cell axis PDG display growth directions. And you can choose what type of heat map and which vectors to display. So stretch max is the value of deformation, the stretch ratio in the maximal direction. And a stretch ratio of 1 means no deformation, 2 means an elongation by 100%, and 0.8 a shrinkage of 20%. And the product of stretch max and stretch mean is equivalent to the areal growth of the cell polygon. So the color and size of the PDG vectors can also be modified. By default, vectors corresponding to the expansion, so stretch ratio more than 1, are displayed in white, while red is used to draw the direction of shrinkage with less than 1. And the threshold parameter is used to display PDGs only in cells for which the anisotropy is above a given value. Now we can move to stack 2. And we can run display growth directions. We can select something like 3, 3. Maybe increase a bit more. Okay. And now you can see the principal directions of growth. So if a cell is growing mostly isodiametric, an X will be displayed. But if the cell is growing mainly in one direction, then it will show this long line, showing that it's elongating mainly rather than expanding in all directions. We can see also here there's quite a high growth, and also here. Then you can save the PDGs with the process mesh cell axis save, this one here. You can call it PDGs, and the maximal and minimal directions of growth will be saved together with the values of deformation associated to them as a CSV file. So we can open it. And you can see the label of the single cell with a different maximum stretch in all the X, Y, and Z direction, and minimum stretch in X, Y, and Z direction with the ratio of the maximum, ratio of the minimum. Okay. You can remove them by doing cell axis clear, and if you want to load them again, you can run cell axis load, select the PDGs, and now you can see them again. And make sure that parent labels are also loaded on the second time point before loading the PDGs.